Hello and welcome to Controllers Tech. This is the 7th video in the STM32 ADC series. In the previous videos we have covered how to read a single channel, and multiple channels using different ADC modes, that includes polling mode, interrupt mode, and DMA mode. We also saw how to calculate the conversion time for the ADC channels. In today's video we will cover the external trigger source for the ADC. Basically we will use one of the timers to control the sampling rate for the ADC channels. I am going to use the same STM32H750 custom development board which I have used in previous videos as well. Let's see the connections once. This is how the potentiometers are connected to the dev board. All the potentiometers are powered with 3.3 volts from the board itself. The outputs from the potentiometers are connected to the 4 channels of the ADC1. We will configure these channels in the cubeMX. I have created a new project for this tutorial. Right now I have configured only one channel of the ADC1. Here you can see the pin PA6 is configured as the ADC pin. Let's configure the parameters now. ADC clock is not an important parameter for this tutorial, so let's set the prescaler to 1, so as to generate a fast clock. The ADC resolution is set to 16 bits. It is very important to keep the continuous conversion disabled. If this is enabled, the ADC will start the next conversion as soon as the first one is finished. If that happens, the conversion will go on continuously, and we won't be able to control the sampling rate. End of conversion is set to single conversion as we have enabled only one channel. The conversion data should be stored in the data register only. There is only one channel for now, and I have set the minimum sampling time for it, that is 1.5 cycles. Now let's check the available external trigger sources for the ADC. If you browse through this list, we have various timers listed here. Choosing the trigger out event of any timer is a better option. This trigger event is easy to configure in the timer. I am choosing the timer 1 trigger out event. Also the trigger edge is set to the rising edge. Before we configure the timer, let's check the block diagram in the H750 datasheet. This diagram helps us determine the clock structure of the MCU. Here you can see the timer 1 is connected to the APB2 bus. Here in the clock diagram you can see that the APB2 timer clock is running at 240 MHz clock. Keep this in mind while we configure the timer 1. Set the clock source as internal clock. Since the timer is connected to APB2 bus, the timer clock is also at 240 MHz. I am setting the prescaler to 24,000, this will reduce the timer clock to 10 kHz. Now if we use the auto reload value of 1000, the timer clock will reduce to 10 Hz. We will use this frequency to sample ADC channel. Here at the bottom you can see the trigger event selection. There are 2 of them, but I am using the first one. Let's set the trigger to update event. Doing this will generate an event each time the timer's counter is reset. This event will trigger the conversion start in the ADC. Here you can see there are 2 trigger out sources available from timer 1. I have configured the first one, therefore the same is set here. We will read the ADC in interrupt mode, so let's enable the ADC interrupt in the NVIC tab. Let's set the pin PA1 as output, so that we can measure the sampling rate on the scope. Alright, that is all we need to configure. Let's generate the project. We will write the main file now. Let's define a 16-bit variable where we will store the value obtained from the ADC. Inside the main function, first start the timer 1 base mode. Then start the ADC in the interrupt mode. Once the ADC conversion is finished, an interrupt will trigger, and the ADC conversion callback will be called. Inside this callback we will read the ADC value, and store it in the variable we just defined. Now toggle the pin PA1, so that we can see the frequency of this loop on the scope. That is all. Let's build the project now. We do not have any errors, so let's launch the debugger. I have added the variable ADC value to the live expression. You can see the ADC value is updating every 100 milliseconds. Well, we cannot be certain about 100 milliseconds, but we have set the timer frequency to 10 Hz, therefore it must be updating every 100 milliseconds. We will confirm this on the scope in a while. I am now rotating the potentiometer in one direction, and you can see the value is reducing. Now I am rotating it in the other direction, and the value is increasing. The ADC resolution is 16 bits, therefore the maximum value obtained here is 65,535. Let me leave it around 60,000. Alright, let's see the toggling frequency of pin PA1 on the logic analyzer. Here you can see the pin toggles every 100 milliseconds. This means that the ADC conversion complete callback is being called every 100 milliseconds. So we were able to achieve the ADC sampling rate of 10 Hz with the external trigger selection mode. The configuration remains the same across other STM32 devices as well, therefore I am not showing it for others. Now we will see the same for multiple channels. Let's open the cubeMX again. Here we will enable 3 more channels for ADC1. Now go to the number of conversions, and set it to 4. The scan conversion mode is automatically enabled. Make sure that the continuous conversion mode is disabled, or else the ADC will start the next sequence of conversion again as soon as the first one is finished. This way we won't be able to achieve the desired sampling rate for the ADC channels. Let's configure the channel ranks. I am setting the minimum sampling time for all the channels. Alright, since we are using multiple channels, we need to use the DMA to transfer the data. Let's go to the DMA tab, and enable the DMA request for ADC1. Make sure the mode is circular, and the data width is configured according to the ADC resolution. Since we are using DMA to transfer the data, the conversion data management should be set to DMA circular mode. Also, we are converting 4 channels now, so the end of conversion should be set to the end of sequence. This way the interrupt will trigger only when all the channels have been converted. This configuration is the same as what we did for the multiple channels using DMA mode, except that the continuous conversion mode is disabled this time. Now finally we need to configure the MPU for the Cortex-M7. Enable the instruction and data cache. Now enable the MPU in the default mode. I have already explained it in multiple channels using DMA video. Basically we will relocate the data buffer to another SRAM, which is located at the address 30 million hex. Here we are simply configuring that region as non-cacheable. That is all we need to configure. Let's generate the project again. Here is the article about the ADC multiple channels using DMA. Here is the part explaining the configuration for the Cortex-M7. Let's copy this buffer definition, and we will paste it in our code. Also we need to create a section in the Flash script file. Now in the main function, after starting the timer, we will start the ADC in the DMA mode. The data will be stored in the ADC value array, and we want to convert 4 channels. When all the channels have been converted, the conversion complete callback will be called. We do not need to read the value, as it is already stored in the array. Here we will simply toggle the pin PA1. That is all we need, Let's build and debug the project. Here you can see all the 4 channels are updating frequently. To confirm the sampling frequency, we can check the PA1 on the logic analyzer. Here you can see the pin remains high and low for 100 milliseconds, which means that the callback is being called every 100 milliseconds. This means that the sampling frequency is indeed 10 Hz. The first potentiometer is set at 60,000. I am rotating the second potentiometer to go around 50,000. Then I am rotating the third one to go around 30,000. And the fourth one is around 40,000. So the ADC channels are responding fine, and the sampling rate is at 10 Hz. Let me demonstrate a different sampling rate now. Here is the timer 1 configuration, and this is the auto reload value we set at 1000. I am changing this value to 10,000. Doing so will reduce the timer clock to 1 Hz, and this will be the sampling frequency for the ADC. So the data will update every 1 second, and the pin PA1 will also toggle at this interval. Let's see the result in the debugger. You can see the channel data is updating every 1 second now. Let's check the pin PA1 on the analyzer. You can see the pin remains high and low for 1 second. So the conversion complete callback is being called every 1 second, and therefore the sampling frequency is 1 Hz. So I hope you understood how the sampling frequency of the ADC can be controlled. Let's quickly see if there is any change in configuration needed for other MCUs. Here is the configuration for the F103C8. Under the external trigger source, we have the events from different timers. You can see the trigger out event from timer 3, so you can use it. We can also use the event from capture compare mode, but this requires a little more understanding of the timer's operation. Since the trigger out events are available in every MCU, we don't really need to look into the capture compare events. But if you want, I can make another video explaining the usage of capture compare mode to control the sampling frequency. Make sure the continuous conversion mode is disabled while using the external trigger source. Otherwise the external trigger is of no use. That is all for this video. I hope you understood how to control the ADC sampling frequency using the timer. You can download the project from the link in the description. Leave comments in case of any doubt. Keep watching, and have a nice day ahead.